You know, there's an invisible force at play right now, this very second, that's keeping you in your seat, letting you hold your phone or mouse, and pretty much stopping the entire world from sliding into total chaos. We rely on it constantly, but we barely ever think about it. So, what is it?
I mean, really think about it. What is that one thing that keeps you from slipping and falling with every single step you did? What allows a pencil to actually leave a mark on a piece of paper? Or, maybe most importantly, what lets the brakes on your car do their job? The answer to all of those is exactly the same.
You got it. It's friction. It is the silent, unsung hero in almost every single thing we do. From something as simple as walking across the room to the incredible engineering that goes into a car. It's one of the most fundamental forces in nature, and today we're going to pull back the curtain and give it the spotlight it truly deserves.
So let's get down to the nitty-gritty. What is friction, scientifically speaking? Well, at its heart, friction is all about resistance. It's the force that pushes back anytime you try to slide one object over another. It always fights against the direction you're trying to move.
But where in the world does this resistance come from? Well, here's the cool part. If you could zoom in, way in on any surface, even something that feels perfectly smooth, like glass, you'd see this wild, rugged landscape of microscopic mountains and valleys. So when two surfaces touch, their tiny little imperfections grind against each other and lock together. That microscopic battle is what we feel as friction.
Now, here's where it gets interesting. Friction isn't just a one-size-fits-all kind of force. Nope, it actually has two very distinct personalities, one that keeps things from moving in the first place, and another that acts on things that are already in motion. Let's dig into this dual nature.
Okay, first up is static friction. This is that initial stickiness you have to overcome to get something moving. You know that feeling when you go to push a really heavy box? That first shove takes the most effort, right? That's because you're fighting to break the powerful grip of static friction. But once it starts sliding, a different and usually weaker force takes over, and that's called kinetic friction.
So you can think of static friction as this stubborn, invisible anchor. And what's really clever about it is that it actually gets stronger to match your push, but only up to a point. Once you push harder than its maximum limit, that anchor finally breaks. It's the reason a book can sit on a tilted table and not just slide right off, almost like it's defying gravity.
And then, once you've overcome that static grip and things are sliding, kinetic friction jumps into the game. This is the force that makes a hockey puck eventually grind to a halt on the ice, or why you have to keep pedaling your bike to keep your speed up. It's the constant, dragging resistance on things that are already moving.
So, what decides how strong this friction is? Why is it so much harder to slide a heavy refrigerator across the floor than, say, a small cardboard box? Well, it turns out friction isn't random at all. It's governed by a few very clear rules.
Okay, so there are three main things at play here. First, the obvious one, the nature of the surfaces themselves. Think sandpaper versus ice. That's a no-brainer. Second is something physicists call the normal force, which is really just a fancy way of saying how hard the two surfaces are being pressed together. A heavier box is harder to push because its weight increases this force, basically mashing those microscopic peaks and valleys into each other much more tightly. And finally, it all depends on the materials themselves. Every pair of materials has its own unique stickiness factor, a number that scientists call the coefficient of friction.
And right here, we can see that special number, that coefficient of friction, in action. That little Greek letter mu just stands for the coefficient. Now just look at the huge difference between rubber on concrete with a static coefficient of 1.0 and ice on ice, which is all the way down at 0.1. That massive difference is why your car's tires can grip the road, but an ice skater can just glide along so effortlessly. But check out that bottom row, our own joints. They are an absolute marvel of natural engineering, with a friction coefficient 10 times lower than ice on ice. It's literally nature's own perfect super lubricant.
So, with all this talk of resistance and things slowing down, you have to ask, is friction our friend or is it our foe? Well, the truth is, it's not that simple. In a lot of ways, it's both. Friction is a classic double-edged sword. On the friend side of things, friction is absolutely essential. I mean, without it, you couldn't walk, cars couldn't drive, you couldn't even pick up a glass of water. The entire world would just be an impossibly chaotic, slippery mess. But on the foe side, friction is a constant battle. It's the enemy of efficiency. It robs our engines of power, generates tons of wasteful heat, and slowly but surely grinds down any moving part over time.
And this is exactly why so much of engineering is just a constant balancing act with friction. Engineers work tirelessly to maximize friction where we desperately need it for control and safety. Think about brake pads and the tread on your tires, but at the exact same time, they do everything in their power to minimize it everywhere else, using things like lubricants and really clever designs to boost efficiency and make parts last a whole lot longer.
So, where does all this leave us? You might think we've got friction all figured out by now, right? But it's actually a huge field of ongoing research and incredible innovation. We are far from done.
Scientists today are exploring friction on levels our ancestors couldn't have even dreamed of. There's an entire field called tribology, which is just the science of wear, friction, and lubrication. Researchers are diving into the nanoscale, where the normal rules of friction start to fall apart and quantum effects begin to take over. They're engineering mind-blowing new materials, like graphene, which is only a single atom thick, that can create surfaces so slippery they are virtually frictionless. The possibilities, from super-efficient robots to new ways to travel in space, are just staggering.
And that leaves us with a really fascinating thought to chew on. For all of human history, we've had this intense love-hate relationship with friction. We need it to stay grounded, but we fight it constantly to be more efficient. As we get closer and closer to truly mastering this force, to engineering a world where we can have near-zero friction on demand, what does that future even look like? What incredible new possibilities are we about to unlock? It's an amazing question, and it's a great reminder that even the most familiar forces around us still hold some pretty incredible secrets.